Cool. Awesome. Hey, everyone. I'm Anish, and today we're going to talk about how to tend and tune your multi-agent reinforcement learning experiments with array and weights and biases. So another name that we can give this is scaling production-grade reinforcement learning. And I'm going to take you to an interesting concept through the current forms of reinforcement learning that we're doing now, and then make our way into the newest forms that LLMs tend to use, and how we can take concepts from reinforcement learning and apply them to agents as we'd imagine them LLMs. But instead of getting ahead of myself, let's go through this part first. And so all of you have probably seen reinforcement learning in some form. For us, we're going to be talking today about drone delivery, or I guess drone flying generally, and autonomous vehicles. And so reinforcement learning generally is a powerful machine learning paradigm that allows systems to learn from interaction. So we usually see this in games to robotics, but now when you have concepts such as multiple agents and across different and more interesting environments outside of the video game realm or specific robotics realms, you can start to see that reinforcement learning can be applied to a variety of use cases. But let's first talk about multi-agent reinforcement learning itself. So quickly, just to show a really technical graphic of here, to simply think about it, as the name implies, single agent reinforcement learning is when a solitary agent navigates an environment. So the agent's actions and the environment's responses are the core of the learning process. But when you have multi-agent reinforcement learning, multiple agents coexist, each with its own strategies and objectives, and this leads to a non-stationary environment, where each of the effects of the agents all act upon the environment, and we have to understand how each of these effects, what the credit is essentially that is assigned from each agent to how they affected this environment. And that's what we try to analyze in multi-agent reinforcement learning. And so there's a lot of scaling problems that come from this. One is that as you make much stricter simulations or requirements for your simulations, your environments also scale in complexity. You also need to worry about the increased need of computational needs as architectures and environments also scale, because you want to run these simulations in parallel across a lot of your GPUs in your clusters. And lastly, it's about learning which techniques the agents should learn such that they could have a nice balance between trying new strategies for the tasks that they're trying to solve, or exploiting the ones that already currently exist for the specific use case that they're trying to solve for. And so when you don't account for these different problems, you end up with autonomous vehicles that consider horse-drawn carriages as trucks. And that is something that we don't want to happen. And so one thing to consider when running through all of these different experiments with your multi-agent setups is that you want a platform that is able to work and minimize the refactorization and increase the developer productivity for taking these models from training and also pushing them into deployment while accounting for each of those scaling issues I mentioned. And so that kind of breaks us down to two fundamental problems. One, having a universal framework to ease the scaling of the distributed workload. And then secondly, ensuring that the people actually building these models, the ML practitioner, have the right set of tools so that they can track their experiments and iterate upon them effectively, so they can reduce the time to market for their different products. And so on the side of Ray, at the very least, we have a nice package called RLLib that's able to help organize the combination of your environments with the learning specifications of your agents and able to emit out and train these different models by distributing it across your workload and your cluster of GPUs. Then you have weights and biases, which provides the full end-to-end developer experience and toolkit to take different aspects of your ML workflow and ensure that at the stage that's effective for your ML practitioner, they have that tool available to them to ensure that they take this model, do the effective training, and then push it to production and then to market. And so this is the one dashboard that we'll look at later. And so in general, this is how you can imagine what it would look like ideally from a user experience to visualize, track, and debug your model pipeline. And I'll show you what that looks like in person by running through one specific example. And so this is also nice if you're using any scale and Ray products, as there's a deep integration from the Ray dashboard to our from our product offering to the Ray dashboard. and the Ray dashboard back to our product. And so to get this behavior, it's as simple as adding into your Ray train, your Ray tune, or your RLLib training itself to add this one line here, the WandDB logger callback. By simply setting this flag with additional keywords such as save checkpoints equals true, at any point of model failure or during the training process, we're able to gather all the metrics to help you identify that failure and restart your experiment from the last effective checkpoint for your models. And so to kind of break this down into a twofold cake a little bit, at the top level of this cake, we have the ML workflow tooling. And that's a direct user experience level that affects the productivity of your ML engineer and your ML team. Secondly, you have the ML execution layer, and that takes care of performance, scalability, and reliability of the execution environment. So something that the coordination of both weights and biases and any scale array do well together by offering this full holistic experience across both the workflow layer and then the execution engine layer. And so this blue box represents traditional training for one-off experiments, while this red box is more of a traditional end-to-end workflow, as most ML practitioners can recognize it, going from data exploration all the way down to model serving. And so let's go look through one specific example. Let's go through autonomous vehicles. So to keep things simple, the idea here that we're going to do is we're going to train an autonomous vehicle to take steps ahead and plan its position in time given its current place in traffic. So for instance, what we do is we gather a lot of LiDAR data from these cars, think like a Waymo car, and we compress it down into a form that we call a bird's eye view. So aka a top-down view that represents all of the different cars, their positions over all time steps. So as you can imagine the scenario, this is a multi-agent scenario. We ourselves are the individual car that's trying to navigate the road, while other cars are also navigating the road, affecting the state of traffic at every moment. So we as our car have to effectively plan for the positions of every other car and also take in the underlying intent of that driver. Are they going to make a turn in the next moment, or will I have to react? And so we need to ensure that we have a full team of developers are able to validate every step of the process before we ensure that this touches the market, because this is a highly critical ML model. If this fails, then people get hurt, and you also get a lot of trouble with a lot of different federal organizations. And so we want to ensure is that we every step of the process, the GPU and cluster considerations for each of the members are organized appropriately to their workflow step. And then we also organize the workflow itself to ensure that every step of the process feeds into the proper team member working on the ML workflow as it matters to them. So for instance, we want to ensure that our data engineer flows the proper data down to our ML practitioner so they can use it for training. And so each and every one of these different objects that are released, so these metrics and this data, all needs to be serialized and centralized in one location for proper analysis. There's no way to debug your model effectively if you can't drill down all the way back to the initial data set that it touched. And so let's go through one of these dashboards. So this is a centralized dashboard that we call a report that you can use to take notes alongside your different ML experimentation. So in this case, you see here, this prediction model contains our current production model for our ML system for planning a autonomous vehicle movement. So in the same report, we're able to frame by frame investigate why our model went wrong. So this actually collection is a little worse. Let's look at this one. I think this one is a pretty bad one. Yeah, and so in this case, the pink dots that you see represent the ground truth of that model and the effective next steps for it, while the blue represents the predicted motion of the specific model. As you can see here in this center model, we predict that this car behind us, this blue car behind the green one, it is, a little too much zoom in on myself, I apologize. You can see that it is predicted to go and hit that green car if we consider the prediction from the model. So our current model is predicting that the car behind our green car is going to hit our car. That is an improper prediction, And so we want to ensure that we can work backwards and debug this process. So going back to our initial collection of our model in our model registry, we can go and click through any part of this process and investigate where in our evaluation or our training any errors occurred. So let's go look at our model registry and see that this is our V0 model currently in production. We can go through and see the files and also the underlying lineage. But I'm going to actually go and look at the evaluation itself. So after looking and seeing the output of all of the different models in comparison, as you can see here, right now we applied a filter. We can remove this filter. It's fine. We can do a comparative analysis of all the different models that we have as candidate models that we want to put to production. Look at the underlying details of these models to see if any glaring errors are consistent, and also do the same frame-by-frame breakdown to understand across all the model architectures that we tried for this specific batch, does it make sense for this specific use case? And if to quickly summarize, this specific architecture where we use a ResNet50 as a backbone as the CNN to investigate the XY position and over the time steps, did awful. And so I would not recommend using this specific backbone. The latency on the communication of weights and biases, or so if you mean from our the ML training to our system, we spin up a separate thread, and so it should be almost not negligent. We offer no real overhead in how we track our metrics. There is a little bit of time that it takes for serializing data because we effectively store in a bucket, and that depends on the size and volume of the data itself. So like how many files and how the size of each of those files. But yeah, I think I can talk about that more a little bit later. Cool. And then also similarly, I can break down and go directly to the model training itself for the associated model in our model registry, and see if was there any issues, not only in our system utilization, like was there a failure that occurred that wasn't caught, but also just see directly, hey, was there a weird spike in my loss curve that I did not account for before deploying this that I missed during my evaluation and promotion process. And so that's like one consistent workflow that you can kind of reuse across a lot of your ML experiments. And so just to recap, these are some like screenshots and different ways you can serialize different assets to investigate your model. So a mixture of rich media overlaid with segmentation masks, or a parallel coordinate plots to investigate hyperparameter tuning options for one specific model. But another use case that we can also talk about is multi-agent reinforcement learning for quad rotor control, aka how to fly your drone. So similarly to our last graph, it's the same workflow, but in this case, we're only looking at training itself. And in this case, we're going to be looking at the concept of having one drone be considered the leader of all the other drones. And in the batch of all these drones, they want to independently understand the position of all the other drones around them, but still be able to follow the main leader one. And so in this case, we use a decentralized actor centralized critic model. So to explain this extremely simply, we think of each drone as an independent agent acting on itself. It knows only its own state and the state of what it's immediately around itself. The centralized critic, however, has a complete understanding of every drone, all of its states, and all of its positions. So the centralized critic is taking a look at the scene of the drones at every moment and seeing, hey, is the placement off from the expectation from the policy that I gave each of these independent agents? And if each of these agents are a little bit off or not following instructions properly, we make an incremental change using PPO. Now, all of this sounds complex, and all of these sound very difficult to implement individually, but actually, nicely enough, RLLib allows you to hot swap a lot of different customizable components. So anything from the OpenAI Firma Foundation Gymnasium environments to the model and action policies that you choose, all of those are easily able to be replaced with a lot of pre-made implementations already provided. So making the decentralized agent centralized critic model is very straightforward from RLLib. And so let's also take a look at a quick example of this. So in this scenario, we have very similar dashboards. What I want to show is that if you have any custom metrics, you're also able to collect that information. So at least in a drone environment, one thing that I take into account is not only the XY position, but because there are 4 motors on a drone itself, there's a mixture of the angle of the drone itself, the amount of movement on each of the rotor, and also the position of the drone at that time. So there's a lot of different aspects that a drone has to consider when to turn itself or to spin one rotor faster. And so you're able to actually, as you should be doing, capturing each of this information. And from weights and biases, you're able to centralize all this information in context in one location alongside, so I apologize for this, I'm not very good at navigating camera zooms in a gym environment. But if I zoom in quite a lot, you can see that this drone flying experiment in very early iterations does not do the best job, but we're also able to capture the movements of each of the drones in context of the video of it itself. So you're able to have this full workflow where you have this qualitative analysis, which is really useful for these more complicated examples where it makes more sense to see with your eyes as opposed to charts. And now I'm going to go and segue into kind of some theory, some like metagame with LLMs now. So right now we're seeing a lot of effectiveness in reinforcement learning human feedback. The concept that we're able to use reinforcement learning principles with LLMs to instruct LLMs to be more human-like and effective in their response. A big core component here being human-like, where correctness may have been the early forms of ChatGPT, but ensuring that we're able to understand the intent of a user who asks via their prompt and able to craft a human-like response is the core aspect of using this reinforcement learning human feedback, where you use a human labeler to score the multiple outputs from a GPT-like model and use that scoring process to train a reinforcement learning model to be really good at saying, hey, a new output from my model comes in, I'm going to guess how a human would score this and ensure that you get that best score always, that best human-like response. So why am I talking about this in the agents talk? Well, that's because LLMs are actually becoming this new backbone for a concept called agent. Now, there is a little bit of overlap and contention if a RL agent and LM agent have this overlap that we are considering. But deep down, a reinforcement using a LLM as an agent is pretty much us saying we want our LLM to be the reasoning layer for understanding the intention of our user and then acting upon it by using either tools or solving for an objective task. So people find this very fascinating and useful. Within these 3 projects alone, there is a shared 70K stars by users from GitHub. And so in these repos alone, these are all agent-based implementations of large language models that take into account a user specification. So like in GPT Engineer or Open Interpreter, you would say something like, build me a program in Flutter to make my personal portfolio, and it will decompose that problem into steps where you will work with it back and forth, a little bit of human feedback in there, to then effectively get the program that you desired. Now, what if we took that one step further? What if we create a whole sim-like environment where we teach each individual LLM agent to learn the best underlying prompt to use for its own goal? What if one agent was really good at programming? What if one agent was a really good project manager, and we allowed each of these agents, through reinforcement learning, to learn these best underlying system prompts, as you probably heard it, to be really good at their specific role and task, and ensure that we use reinforcement learning to also ensure that it learns the right policies to understand how to return human-like and reasonable responses to a lot of these scenarios that we would propose in this simulated Pokemon-like town. And that's because, at the end of the day, this is a broken down code form of what these agents are doing. It's perceiving our task, storing it to memory, retrieving the best collection of documents or memories, a RAG talk coming to you later, we'll explain this better, and ensuring that it knows the best plan and actions to take. So reinforcement learning is, in effect, how can we optimize a policy to know which best plan and action to take. So this is not done yet, this generative reinforcement agent, but I hope someone does it soon, and they use us. And the reason I say this is that with the proliferation with open source models and the investigation to debug and monitor the usage of your LLM, there's a natural synergy occurring for LLM ops. So now ML ops and LLM ops will now intersect in very interesting ways, and Weights and Biases is here for it. And so to quickly end off, I'll flash some screens of some of our new products that we can talk to about offline later. But this example of that agent session I was talking about with Open Interpreter, where I told it to do, I think, some really dumb task. Let's see. I told it to get the last summary of latest LM articles from RxIV. Underneath the understanding from that, it provided me a plan and the steps of code, so a mixture of arguments and input, to essentially say, here's the plan of attack I'm going to take, and here's the code I'm going to execute on your computer. Do you agree? And from here, you can start the debugging process. Similarly, if you're building applications that you want to use to monitor your LLMs, like in the case where you want to ensure that you convert all of your text and remove PII, you can do so effectively and have a central place to interactively understand and pinpoint situations where LLM safety considerations, such as preventing PII to be released, occur. And so that is my talk. Sorry. Yeah. Here is the Weights and Biases core again. Thank you, guys, and feel free to connect on any one of these forums.